Hi, me again. Let's look into finding the dimension that a set spans, right? So you want to find the dimension that a certain set spans. So let's see what that means. So from 4.4 we learned that the set of all, the span of S, right? The span of S is the set of all possible linear combinations of the vectors in the set. What does that mean? What is a linear combination? It means if you multiply this times a number and you add it to this times whatever number you want, then you do this infinitely many times, you're going to generate the span of S. So let's see. If I multiply 1, 0, 0 by anything I want, positive, negatives, irrationals, then what do I get? Then I'm going to get, let's see, this is the vector 1, 0, 0. Then if I multiply by negative 1, I'm going to get a vector in the opposite direction. By positive 2, I get this vector. By negative 2, I get some vector there. So by adding, so if I add this plus this, I'm going to get this vector. So whatever combination of these vectors I add together, I am going to land on this line that goes through the origin, right, through 0, 0, 0. So those of you who have not had Calc 3, this is how you would draw this vector 1, 0, 0 in 3 dimensions. So the question is, what is the dimension that that the set spans? Well, that's another way to ask that is, how many of these vectors are really needed to span the same set? So if I add this vector plus this vector, I'm going to get this vector. So 3, 0, 0 is not really necessary, it's redundant, right? Because I can get the same space by multiplying this guy by numbers. I don't really need 3, 0, 0. If I were to multiply 1, 0, 0 by 2, then I'm going to get this vector. So that means this is also redundant, right? So all of these 3 vectors line up in a line. They're all these are scalar multiples of 1, 0, 0, which means you only need 1, 0, 0 to span the same space. So the set of all linear combinations then is going to have dimension 1, because you only need one of the 3 vectors to span the same space as you would all 3 vectors. Or you can say, I can express this as a linear combination of that vector, so this is redundant. I can express this as a multiple of that vector, so this is redundant. So you really only need one vector. So here we're going to say the dimension of the span of S is 1. Now, if you think about it, all multiples of 1, 0, 0 line up in a line. So the dimension of a line, geometric dimension of a line, is 1, right? So this is the set of all real numbers. It's just the number line, right? And the dimension of the number line is just one-dimensional. Now, if you look at the set 1, 0, 0, 1, 2, 0, 0, 1, 0, so just by inspection, you see that one of them is redundant, right? So the vector 1, 0, 0 looks like this. So it's 1 on the x-axis and 0 on the other axis. The vector 0, 1, 0 looks like this. So this visual is supposed to help you. You do not need to know how to draw these in general. Now, if you do 1 times vector 1, this is vector 3, this is vector 2. So you see that vector 2 can be expressed as a linear combination of those other 2 vectors by doing 1 times vector 1 plus 2 times vector 3. So that makes V2 redundant, right? So if you can express one vector as a linear combination of the other 2, that one vector is redundant. You don't really need it to span the same space. So what does that mean? Well, here, vector 2 is going to be 1, 2, So it'll be this vector in the xy plane. So that still doesn't answer my question, what is the dimension of the span of this set? Well, it's the dimension of the span is the set of linear independent vectors in your set. So if you remove this, are the two vectors left over linearly independent? So we have a way to test that doesn't involve computation. If one is a multiple of the other, right, a scalar multiple of the other, then they are linearly dependent. And clearly, V3 is not a multiple of V1. So these two vectors are linearly independent. So you have two linearly independent vectors. That means the span of S has dimension 2. So I'm going to rewrite that as the dimension of the span of S, that's equal to 2. All right, so what does that look like geometrically? So you're done with the question, that's it. We answered the question. But to visualize what the span means, well, the span of S is every possible combination of 1, 0, 0 and 0, 1, 0. That means if I multiply 1 times V1 plus 1 times V2, I get this vector. I multiply V1 times -1, I get this vector. I multiply both of them by negatives and add them together, I get this vector. So by multiplying both V1 and V3 by constants and adding them together, I can get any vector in the xy plane, right? So the span of S is the xy plane. So geometrically, the span of S is the xy plane. I don't need to know this in order to answer the question. I already answered the question, but it's nice to be able to visualize it. So the span of S is every possible, is the space that you get by multiplying V1 and V3 by constants and adding them up in every possible way for any possible constant. So that's going to span a whole plane. A plane is two-dimensional, right? So the dimension of a plane is 2. So that especially because you have two linearly independent vectors there. So this example 3 is similar to, I think, problem 69 and 70 in your homework. So you want to figure out how many vectors are necessary to span this space. Now, this space is really given to us in terms of its general term, right? So this is a general vector in this space. So it looks like what I can do with this, so this is embedded in R4 because it has 1, 2, 3, 4 coordinates, right? So this, the set W is all possible vectors. So you assign C and D all possible values. So C and D sound like scalars, right? So here's what I'm going to do. I'm going to split this up into D's and C's. So I'm going to take that one vector and I'm going to split it up into everything that has D's in it. So that's D, negative D, 0 because there's no D here, and positive D, plus there's no C's here, so that's 0, C, C, and a C for this. So if I add these two together, I'm going to get that vector. So now I can also write this as D times, I factor out the D, right? 1, -1, 0, 1, plus I factor out a C, 0, 1, 1, 1. So now the space W is the set of all possible combinations of these two vectors, right? So that's what C and D can be any real numbers. And so the space W is all the linear combinations of these two vectors. Now these two vectors are linearly independent independent because they are not multiples of each other, right? We had a theorem right at the end of 4.4 that says if the two vectors are scalar multiples, if and only if they're linearly independent. So W, I'm going to say that in words, is all possible linear combinations of these two vectors, 1, -1, 0, 1, and 0, 1, 1, 1. Because these two vectors are linearly independent, since these vectors are linearly independent, they form a basis for the span of W. They form a basis for W, really. And so the dimension of W is 2, right? So W is spanned by two linearly independent vectors. That makes the dimension of W 2. Hope that helped.